Hello students, good evening everyone. I hope all are doing well. Welcome to Infinity Learn by Sri Chaitanya. This is me Surya, your chemistry faculty from Infinity Learn. So here we are going to discuss about the next part of the chapter, that is about the periodicity in properties. So in the last two classes we have been discussed about the classification of elements, right? The first part of the chapter. So we have seen the classification of elements from the starting of Dobrynin's triads, Newland's law of octaves, Mendeley's periodic table and Moseley's periodic table. Then we have seen the classification of elements in the different blocks, right? How to predict the position of an element in the periodic table. So here we are going to discuss the next part of the chapter, that is periodicity in properties. So what do you mean by the periodicity? Is there any idea? So something is repeating, right? So periodicity means something is repeating. Here some of the properties are repeating in a regular interval of time or regular period of time, right? That is known as the periodic properties. So here in this chapter we are going to discuss about these much properties, how they are affecting or how they are changing in a group as well as period. We have seen, right? In the case of the periodic table, we will be classifying those elements into 18 groups and 7 columns. I mean 7 periods, right? 7 periods as well as 18 groups. So how these properties like atomic radii, metallic and non-metallic character, ionization enthalpy, electron gain enthalpy, electron affinity and electron negativity, how they are changing in a group as well as period. These are the periodic properties of elements. So here in this particular session, we are going to discuss these two properties only, that is about the atomic radii, then metallic and non-metallic character. Now let us start with the first property, that is atomic radii. Is there any idea about the what do you mean by radii or radius? Yes, it will be distance, right? So the atomic radius is the distance between the center of the nucleus and the outermost electron of an atom. For example, if you are representing an atom like this is our center of nucleus, right? This is our nucleus, and there will be some electron in the orbit, right? These electrons are revolving around the circular path, that is known as the orbit. So if you are taking the distance between center of the nucleus, I mean center of the atom or the nucleus to the electron, that distance is known as the atomic radius. Clear? So we can define the atomic radius as the distance between the center of the nuclei to the outermost electron of the atom. So this size of an atom is very small, right? Because atom is very small, if you are finding the measurement also, it will be very small. For example, you can see here, lithium is having the atomic radius in terms of angstrom. Maybe you will have idea about what you mean by angstrom, right? This is 10 to the power minus 10, which means that much small amount is there. So if you are taking the atomic radius of lithium, it will be 1.52 angstrom. And for sodium, it is 1.86 angstrom. Potassium, it is 2.31 angstrom. Rubidium, 2.44 angstrom. And cesium, it is 2.62 angstrom. Which means that the radii of atom is very small. Clear? Now in the case of atomic radii, according to our syllabus, we need to focus about the 3 different types of radii. First one is covalent radii, right? Covalent radii. Then the van der Waals radii. Then the metallic radii. We can discuss one by one. We can start with the first type of radii, that is the covalent radii. So what do you mean by the covalent bonds? There will be 2 types of bonds, right? One is ionic bond and the covalent bond. So in the case of covalent bonds, it will be the sharing of electron is happening, right? So here the covalent radius is also defined at the distance, but the distance is the half the distance between the centers of 2 nuclei, right? In which a covalent bond is formed by the sharing of electrons, right? Sharing of electrons in 2 atoms. So for example, if I am taking the 2 atoms here, 2 nuclei is present, right? So here if you are taking this distance between these 2 nuclei, those half distance is known as a covalent radii, right? Clear? So this will be the total distance in between the 2 nuclei of the 2 atoms which are overlapping, right? Which are overlapping. So the half of this distance is known as the covalent radii. If the distance is taken as d, then the covalent radii will be equal to d by 2. Clear? This is the first type of classification of atomic radii in the case of non-metals. So we have already discussed the type of, what do you mean by the metals and non-metals in the chapter metals and non-metals, right? So here this radii is applicable for the non-metals. Now what about our next radii? What will be our next radii? Yes, metallic radii, right? Metallic radii. So from the name itself you can identify that it is based on the metals, right? Based on the metals. So what you're observing here, again this is also half the internuclear distance between the centers of two adjacent metal atoms in the metallic crystal, right? It is applicable only in the case of metals. So what you're observing here, these are two metals that are comparing, right? So this is our nuclei of first metal, this is the nuclei of another metal. So if you are taking the distance, this distance is known as the representation as d here. Then if you want to find out the metallic radii, it will be the half of this distance, which means it will be d by 2. Clear? Then this is applicable for the metallic crystals. So this radius is also known as crystal radius. Clear? Fine. Now the last case, van der Waals radii. So what you're observing here, I will give you an image here. There is no any overlapping, right? These two atoms are separately given here. So this is the case of solid state. So when atoms or molecules of an element are closely packed in the solid state, they are held together by weak attractive forces, right? Weak attractive forces. These forces are known as the van der Waals forces. I know that this will be a new term for you, but you need to focus on the van der Waals forces here. So how we can divide the van der Waals radius here? It will be the half of the distance, right? It will be the half of the distance between the centers of two different molecules. Centers of two atoms or two different molecules, right? Which are closest to each other in the solid state. So this van der Waals radii is applicable in the case of solid state. So these are the half the distance between the two atoms of the different molecules, which are the closest distance here, right? So this will be the total distance, and the half of d is equal to the van der Waals radii, which is given as RVDW, stands for van der Waals. Okay, I hope you understand about the difference between covalent radii, metallic radii, and the van der Waals radii. These are all about the atomic radii. Now we need to move on the periodic properties, right? How these atomic radii changes in the case of group as well as period. Then one more question. If you are taking the rate of van der Waals radii, covalent radii and metallic radii, which one will be higher? Which one will be higher? It will be van der Waals radii, right? So there is a point that whenever overlapping is higher, right? Overlapping is higher. For example, in the case of covalent radii, first radii, we have seen that there will be overlapping, sharing of electrons, right? So whenever the overlapping is very higher, the atomic radii will be very less, right? Clear? As the overlapping increases, atomic radii will be very small. So in the case of covalent radii, there will be maximum overlapping. So they will be having the very less atomic radii as according to this relation. Then metallic radii, then one which is having the maximum value of atomic radii. Maximum value of radii is van der Waals radii. Clear? Now let us see how these atomic radii is changes in a group of a periodic table. It gradually increases from top to bottom in a group, right? If you are moving from down the group, what is happening to the atomic size? It increases. So what will be the reason? The atomic radii is directly proportional to the number of shells, right? Number of shells. So for example, if you are taking the group 17, group 7a or group 17 elements, it will be fluorine, chlorine, bromine and iron, right? But you're observing here, size increases, which means that in the case of fluorine, there will be only 2 shells, right? For chlorine, it will be 3 shells, then bromine 4 shells and iron 5 shells, which means as we are moving down, number of shells increases, which means size increases, right? Clear? So for example, if you are taking the first group element, lithium, sodium, potassium, rubidium and cesium, right? So what you are observing? Lithium is having very less size, then cesium is having the very high size, right? Because they are moving from top to bottom in a group. So how we can predict here? And also the value is already given here. Lithium is having very least 1.23 and cesium is having highest value, that is 2.35 angstrom. Clear? So what will be the reason behind that? Already given here. For lithium, if you are writing the shell electronic configuration, it will be 2, 1, right? 2, 1, which means only 2 shells are present, right? So if you are moving to the sodium, it will be 2, 8, 1, which means 3 shells are present. 3 shells are present. As we are moving down, number of electronic shells increases. Number of electronic shells increases, right? So the valence electrons held less strongly to the nucleus with the addition of repulsion of electrons in the electronic shells. No need to confuse here. So whenever we are moving to the top to bottom in a group, right, number of shells increases. So what will be the attraction between these last electron and the nucleus? Whether it is high or low, as the size increases. Low only, right? They held very less strongly to the nucleus. That is where we are expressing here. That is why atomic radii increases, right? Atomic radii increases or the size of the atom increases. Clear? Simple point is that when you are moving top to bottom in a group, when you are moving down the group, what is happening to the elements? Their number of shells increases. As the number of shells increases, there will be very less attraction between the last electron as well as the nucleus. That is why they are having the very high size. Clear? Now, what will be the trend of atomic radii in the case of a period when we are moving from left to right in a period? When we are moving from left to right in a period. So here, this is our first period element, right? Sorry, second period element, not first period. The first period, there is only 2 elements, hydrogen and helium, right? So this is our second period element, right? Lithium. Then beryllium, boron, carbon, nitrogen, oxygen and fluorine. So what are observing here? Size increases or decreases from the image? Yes, decreases, right? So in the period from left to right, atomic radii or atomic size decreases. So what will be the reason? Yes, you can see over here the atomic radii is inversely proportional to 1 by effective nuclear charge. So if you are taking proportional into 1 by effective nuclear charge, it will be understood that it is inversely proportional. Clear? So what do you mean by the effective nuclear charge, which is already given? It will be the total number of protons. The total number of protons is simply known as the effective nuclear charge. So what is happening to the period? So here in the case of period, what is the number of proton? Only 2 proton, right? And what about the beryllium? It is B. So what will be the atomic number? The atomic number will be similar to that of the number of protons, right? So lithium, the atomic number is 3 here, so 3 protons. Then for beryllium 4 proton, boron 5 proton, carbon 6, nitrogen 7, oxygen 8, fluorine 9, right? Which means as we are moving from left to right in a period, the number of protons of the effective nuclear charge increases, right? So when we are adding more electron to the particular shell, consequently the electrons are increasingly attracted, which means that no need to confuse here. Whenever we are adding more electron to the shell, right? When we are adding more electron to the shell, because of their protons, they will be having strong attraction, right? Strong attraction towards the nucleus, right? Clear? Are you getting my point? Here, all the elements in the second period, there will be only same shell, right? But when we are moving from when we are moving from left to right in a period, what is happening here? Number of protons increases, which means that only proton is increases, it is belong to the same period. So if you are adding more electrons, they will be having the strong attraction. Because of the strong attraction, size will be decreases, size will be reduced, right? That is why we are saying like that. From left to right in a period, atomic radii decreases. Okay, I hope you understand. Now this is a graphical representation of second period elements, right? Second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So what are you observing here? The atomic radii, which is given in the y-axis, is decreasing, right? It is decreasing. Then what about the case of group? We are taking the second group element, right? Lithium, sodium, potassium, rubidium and cesium. When we are moving top to bottom in a group, size increases, right? From lithium to cesium, size increases. This is simply the graphical representation of periodic property of atomic size in period as well as group. and this is in the case of groups. Okay, I hope you understand. So again, just giving the representation of the atomic size in the period as well as group in the complete periodic table. First group, this is the first group and this is the first period, second period, third period and fourth period respectively. Clear? Now again, chemistry is the case of exception, right? So here in the case of atomic radii in a period, there will be some exception, right? So if you're asking about the atomic radii of inert gas, right? Inert gas means when you are moving from top to bottom, left to right in a period, right? Left to right in a period, according to our general trend, there will be having the very less size, right? For example, helium, neon, argon, krypton, xenon and radon is having very small size. But here in actual practice, the atomic radius of an inert gas is the largest in this period. Why? Because they are considering as the van der Waals radius, not about the simple atomic radius, right? Okay, I hope you understand. So if you are having any question about these type of question, this is the one exception in the case of periodic table. In general, in the case of period, if you are moving from left to right in a period, what is happening to the size? Size decreases, right? But in the case of inert gases, even though they belong to the extreme right of the period, right? Extreme right of the period, they will be having the size very less. But in actual practice, these inert gases having the highest size. Clear? So the values are given here. Neon is having the maximum size of 1.60 as compared to all other elements in the second period because of their radius is expressed in terms of van der Waals radii. Okay, I hope you understand. Now the next one is the another type of radii, that is known as the ionic radii. So what do you mean by the ions? How ions are forming? Either losing electron or gaining electrons, right? So if you are losing electron, you will be getting the cations. If you are gaining electrons, we will be getting the anions, right? So here the distance between the nucleus and the point up to which the nucleus shows the influence in an ion is known as the ionic radius. There is no need to get confused with the statements given here. Simply, it is the distance between nucleus and the ions, right? Nucleus and the electrons in the ions, that is known as the ionic radii. Now, what do you mean by cationic radii? For example, if I am taking sodium, right? Sodium is forming sodium plus ion plus 1 electron, right? So by losing electron, it is getting a charge of positive, that is, they are known as a cation, right? So loss of electron gives cations. So for the cation, this ionic radius is particularly named as cationic radius, right? Cationic radius. So what you are observing here in this box? If I am taking the lithium pure atom, right? Lithium parent atom, it will be having the atomic radius 1.52. Then what about the case of Li plus? It is 0.76, right? 0.76. Then for sodium, it is 1.86. Sodium plus, it is 1.02. Potassium 2.31. Potassium plus, it is 1.33. Then rubidium 2.44, but the cation it is 1.48. Then for cesium 2.62 and cesium plus it is 1.69. So what you are observing here, if you are asking about the cationic radius, that is compared to that of the pure atom, it will be less, right? I hope you understand the point. So the radius of cation is less than that of the parent atom from which it is formed. Why? Because they are losing the electrons, right? They are losing electrons. So if you are losing electrons, then there will be strong attraction. So size decreases, right? Cationic size decreases as compared to that of the pure atom or the parent atom. Now what will be the case of anionic radius? More electrons are adding, right? Gaining of electrons will result in the anionic radius, right? For example, if I am taking chlorine, chlorine is gaining 1 electron to form chlorine minus ion, which means it is an anion, right? So gain of electron gives anions. So the particular radius of the anion is known as the anionic radius, right? Anionic radius. So what will be the value of anionic radii, whether it is higher or lower than that of the pure atom? Yes, it will be higher, right? It will be higher because more electrons are adding. So there will be more electrons are adding, so size will be very higher, right? Size will be very higher. So the radius of O2 minus ion is greater than O minus than the pure or parent oxygen atom. Clear? So simply the reason is given here. The same nuclear charge in an anion adds more number of electrons. The effective nuclear charge per electron decreases and hence electrons are less strongly attracted in an anion, right? So if you are adding more electrons to the same shell, there will be the very strong attraction between the nucleus and electron, right? That's why they are having the very high size, right? Very high size as compared to the present atom or the parent atom. This is about the cationic and anionic radii, so simply the ionic radii. Now based on that, you will be having a question here. Try to answer this question. The increasing order of the atomic radii of silicon, sulfur, sodium and magnesium and aluminum is. First try to understand the position of these elements, right? First one, it is sodium. Sodium is having 11. Then after sodium it is magnesium having the atomic number 12. Then aluminum with atomic number 13, right? Then what about the next element? Silicon and sulfur, right? Silicon and sulfur. Silicon is having the atomic number 14 and sulfur is having the atomic number 16, right? So these are moving from left to right in a period, right? So what is happening to the size? Size decreases, right? So what will be our correct answer? It will be option A, right? Sulfur is having very less size, then silicon, then aluminum, then magnesium and sodium. Sodium will be having the maximum size. That means option A will be our correct answer. Now here is our next question. Find out the increasing order of O2 minus, F minus and Na plus and Mg2 plus ion. So here different ions, cations as well as anions are given here. We need to identify the correct increasing order of ionic radii, right? So how we can answer this question? As we already know, anionic radii is higher than that of the cationic radii, right? So when you are taking anionic radii, it will O2 minus, right? First we need to identify the increasing order, right? Increasing order means it will be starting from the least one. So which one is having the very least radii here? It is Mg2 plus, right? Mg2 plus means 2 electrons are removing there. Mg2 plus is having very less. Then next cation, that is sodium plus, right? Then what about next one is anionic radii, right? If anionic radii means if the more number of electrons are lost, then they will be having more atomic radii. So here F minus means 1 electron is gaining, right? 1 electron is gaining. So it will be F minus. Then for O2 minus means it is 2 electrons are gaining. So it will be having the maximum size. So this will be the correct increasing order of ionic radii of O2 minus, F minus, Na plus and Mg2 plus ion. Okay, I hope you understand. Okay, just try to answer this question. The correct increasing order of the ionic radii is here Cl minus, Ca2 plus, K plus and S2 minus n is given here. Just as that of the last question we have discussed, try to solve this question. Try to take it as an homework. So option D is the correct answer. You need to check whether you are getting the same answer or not. Then which of the following has the largest atomic radius? Largest atomic radius. So these are the atomic numbers given here: aluminum, silicon, chlorine and sodium. So which one is having the highest atomic radius? Yes, these elements are belong to the same period, right? Same period means left to right size decreases. So here from sodium to chlorine size decreases, which means that sodium will be having the highest size, which means option D will be our correct answer. Clear? Sodium is 11, then aluminum is 13, right? Silicon is 14, and last one chlorine, it is 17. These are the part of a same period, right? Same period, left to right size decreases. So this will be the order. The next question, which of the following species will have the largest and the smallest size? Largest and smallest size. As we already know, cationic radius will be very less and anionic radius will be very high, right? So among the size here, we need to identify which one is having the largest and smallest value. Magnesium, magnesium 2 plus, aluminum and aluminum 3 plus, right? So aluminum 3 plus is having very small size, right? Aluminum 3 plus is having very small size. Then, so we will try to find out the radii here, Al3 plus, then Al, then Mg2 plus, then Mg, right? Clear? Here 3 electrons are removing, so it will be having very less size. And again, parent atom is aluminum. Then after that Mg2 plus, right? Mg2 plus 2 electrons are removing. Then last one Mg. So largest one will be magnesium and smallest one will be Al3 plus, right? Option A will be our correct answer. Okay, that's all about the atomic radii part. We have seen the covalent atomic radii, covalent radii, van der Waals radii and metallic radii. Then we have discussed about the ionic radii and the ionic radii in the different types like the cationic radii as well as the anionic radii. Now we are going to discuss about the next property, that is about the metallic character and the non-metallic character. So what do you mean by the metallic character? We have already studied in the case of metals, right? What do you mean by the metals? How metals are forming? So here metals or metallic character is refers to the tendency of an element to lose electrons, right? So if you are losing electron, you will be getting cations, right? We will be getting cations. So the ability of an element to form the cations is known as their metallic character. Clear? So if any of the metal, any of the element is having high metallic character, means they will be easily lost the electrons. So that metals are considered as metals are having the high metallic character, they easily lose electrons. So what are observing this image? What are observing this image? This is our sodium metal, right? This is our sodium metal. So in the case of sodium metal, 11 electrons are present, right? If you are taking this outermost electron, right? If you are losing this outermost electron, what you are observing? It is Na plus ion, right? Na plus ion, which means size is decreasing here, right? Size is decreasing here. And this property of this element of losing electron is known as the metallic character, right? Metallic character. Okay, I hope you understand. Now what do you mean by the... Okay, then we need to check about the metallic character. What is the trend of metallic character in a group as well as period? So in the case of a group, the metallic character increases from top to bottom in a group. So what will be the reason? Top to bottom in a group, it is increases, right? What will be the reason? Yes, it is given, right? So as we move down a group, the atomic size increases, right? Atomic size increases due to the addition of energy levels, which we have seen the first slide when we are discussing about the atomic radii, right? So it is making it easier for an atom to lose electrons. Okay, I hope you understand, which means that if you are moving from top to bottom in a group, size increases, right? As the size increases, the attraction of these last electron towards the nucleus is very less. So it can easily remove the electrons, right? It can easily remove the electrons. That is why the metallic character is increases down the group. Then, what do you mean by the non-metallic character? Just opposed to this, right? Here this is about the group, right? If you are asking about the period, what will be the trend for metallic character in the period? Opposite. So it will be decreases, right? So if you are moving from left to right in a period, size decreases. Size decreases means there will be strong attraction of electron as well as the nucleus. So that there will be very strong attraction. There is very difficult to remove those electrons. That is why they are having very less metallic character. Clear? Again, it is given here as we move across the period, atomic number increases, nuclear charge increases, and the electrons are more strongly attracted to the nucleus. So it is very difficult to lose those electrons. That is why metallic character decreases along a period from left to right, right? Now, what do you mean by the non-metallic character? Metallic character means tendency to form positive ions or the cations by losing electron. In the case of non-metallic character, it is the tendency to gain electrons to form the negative ions known as the anions, right? Tendency to gain electrons and form negative ions or anions. So what are you observing here? This is our fluorine atom, right? Two, 7. So if you are entering one electron to this element, it will be forming F minus ion. Total 2, 8 electrons are forming, right? So they are forming an anion known as the fluorine anion. Clear? That is the non-metallic character. This property of this fluorine metal is known as a non-metallic behavior, or fluorine is a non-metal, right? Now what will be the trend in the period and group for a non-metallic character? It is just opposite to the metallic character, right? So if you are moving from top to bottom, if you are moving from left to right in a period, what is happening to the metallic character? Metallic character decreases, right? So obviously non-metallic character increases from left to right in a period. So if you are focusing on the periodic table, we can say that from left, extreme left of the periodic table, it is 1 and 2 group elements. They are alkali metals and alkaline earth metals respectively, right? Which means that they are having highly strong metallic character. So when you are moving from 13 to 18, when you are moving from p block elements, you can say that the topmost right element is having the non-metallic behavior, or they are non-metals, right? Clear? The same reason is already given here. Across the period, atoms become small, or their size is very small. So ability to gain electron increases. That is why their non-metallic character increases. So what about the case of group? Down the group, metallic character increases. So that non-metallic character decreases from top to bottom in a group. What will be the reason? As we move down the group, atomic size increases. There will be very less attraction between the electrons and the nuclei. So it is very difficult to gain extra electron to that, right? Gain extra electron to that, or additional electron to the increase the distance and the shielding effect, which we will be discussing in detail in the case of D block elements, right? So this is the reason why non-metallic character decreases from top to bottom in a group or down the group, right? So this is the pictorial representation of the complete periodic table. What is happening to the metallic character and what is happening to the non-metallic character from left to right in a period, right? Left to right in a period. So here it is given left to right in a period. Non-metallic character increases and metallic character decreases. Top to bottom in a group, metallic character increases, non-metallic character decreases. Clear? Okay, now let us practice some questions based on the metallic character and behavior. The correct decreasing order of metallic character is correct decreasing order of metallic character. Just focus about the trend of metallic character in a group as well as period. The options are given here: potassium, beryllium and calcium, right? So beryllium and calcium is belong to the same group, right? When we are moving top to bottom in a group, what is happening to the metallic character? It increases, right? So calcium is, so option C is our correct answer. Calcium is having more metallic character, right? Than beryllium, right? Now one more case is here, potassium. So potassium and calcium is belong to the same period. If you move from left to right in a period, what is happening in the metallic character? It decreases, right? It decreases, which means that potassium is having very less atomic radii, right? 1 second. So beryllium and calcium is having metallic character increases from top to bottom in a group, right? So what is happening here? If we are comparing beryllium and calcium, calcium is having more metallic character, right? Calcium is having more metallic character than beryllium, right? Than beryllium. Then what is about the potassium? What is about the potassium? They belong to the period, right? If you are moving from left to right in a period, what is happening to the metallic character? It decreases, right? It decreases, which means if you are comparing potassium and calcium, calcium is having the metallic character more, right? So calcium is having very less here. So potassium, calcium and beryllium will be the correct answer here. Here is the next question. Which of the following represents the correct order of metallic character? Just like this same question, you need to try to understand the answer for this question. Take it as an homework. The 4 different elements are given here: silicon, beryllium, magnesium and potassium. Just like the previous question, we need to identify the elements which is they are belong to same period or same group. Then what is happened to the metallic character? Yes, metallic character in the period as well as group, right? Then you will get the correct answer as option A here. Okay, that's all about from my side for today. So we have just discussed about the classification of elements and periodicity and properties, right? So here in this session, we have been discussed about the periodicity and properties, right? We have started about the atomic radii. In the case of atomic radii, we have seen the crystal radii or the metallic radii, van der Waals radii and the ionic radii, right? And also the covalent radii is also discussed, right? Then in the case of next part, we will be discuss about the metallic character as well as the non-metallic character, right? We have seen the metallic character is increases down a group and decreases along a period, right? The non-metallic character increases along a period and decreases down a group. So we have seen some questions also based on the property. The next class we will be discussing about the another properties like electron gain enthalpy and ionization enthalpy, how they are affecting in a group as well as period. Okay, I hope you understand the session. If you have any doubt, you can ask in the next class also. So if you really like the session, hit the like button and share the session to your friends also. Subscribe our channel. If you want to get the session PDF, you need to join our Telegram channel. So thank you so much all of you. See you in the next class. Bye bye.